My name is Dr. Alex Badges, and I am the staff quantitative ecologist and data scientist for MASERC, the Minnesota Aquatic Invasive Species Research Center here at the University of Minnesota. In this video, I'll be describing how to use a very cool computational approach called optimization modeling. To frame that lesson, I'll use an example from a research project here within MASERC being led by Drs. Robert Haight and Amy Kinsley, which is aimed at understanding how to place watercraft inspection stations at different lakes in the state of Minnesota to prevent the spread of harmful aquatic invasive species. The aim of this video is for anyone to be able to follow along to learn more about optimization modeling, invasive species, and watercraft inspections, even if these topics are new to you. To start, I'll note that Minnesota is colloquially called the land of 10,000 lakes, but even this title sells our state short. We actually have more like 12,000 lakes, according to the Minnesota DNR. Not surprisingly, then, lakes are a huge part of our state's economy, ecology, and cultural heritage. To focus on just one aspect of how we interact with our lakes here, by one reasonable estimate, recreational boaters make approximately 1 million lake-to-lake trips each calendar year within the state. Here I'm defining a trip as one in which a boater launches their boat in one lake, takes it back out, moves to a different lake within the state and relaunches it there within the same year. These trips or movements of boats between two different lakes are particularly interesting to us here at MASERC because they connect even far apart lakes within the state in some meaningful ways they probably otherwise wouldn't be connected in. And one negative way they connect lakes is that they may result in the spread of aquatic invasive species. Before we go any further, I'd like for us to consider what is an invasive species. Maybe you've heard this term before, or maybe you haven't. Maybe you just know that invasive species are bad in some way. Either way, I think it's actually interesting that the official definition of an invasive species is pretty complex. Here's at least how I prefer to define one. An invasive species is an organism from far away that establishes and thrives in a new area, and as a result, may cause unusual harms to that new region's systems. So, for a species to be truly invasive by this definition, it has to be somewhere new that's far from its original home. It has to just not establish but thrive in this new spot, and it has to, through that success, do harm to its new region that is far above what is normal. What do I mean by that last requirement? Well, consider that predators eat prey, right? That's obviously harmful to the prey, but it's normal harm. It's when a new predator is capable of eating all the available prey in a new region so that no one else can get any, for example, that we have a problem. As all of those requirements in that definition hopefully imply, the odds are actually against any species becoming invasive. First off, it's hard for most organisms to move to very far away places. Even if they do, it's often hard for them to survive in those new places. Most organisms that get moved to a new place don't survive at all, and many who do survive only barely survive. Those that do establish, though, rarely succeed beyond what would be considered an average amount. And even those that do thrive don't always cause enough harm to be considered invasive. They just become sort of new members of their new community. So it's a very small percentage of organisms that become invasive. It'd be on par with a species winning the lottery, really. And yet today, we have dozens of aquatic invasive species living in Minnesota lakes, and more arrive every year. How are those two realities possible? Well, as this map of global shipping routes shows, we humans move around a lot, incredibly long distances in some cases. Either by accident or on purpose, we move organisms around a lot with us too. This means we are buying potential invasive species thousands of lottery tickets every day. When you do that, some of them are unfortunately bound to win. So our goal as AIS warriors and defenders here at MASERC is to prevent new invasives from establishing in our lakes and to prevent those already here from spreading, just as a doctor wants to prevent a disease outbreak or at least keep one contained. This means we need to intercept as many risky boats as they move between lakes as we can. What do I mean by a risky boat? That is a term we use a lot here in MASERC, and we have a specific meaning in mind when we say it. This is a boat making one of those lake-to-lake trips between two lakes, specifically from a lake already possessing one or more invasive species and headed to a lake that's lacking at least one of those same invasive species. So if you think about this like it's a disease, you have a sick lake and a susceptible lake that are being connected by the movement of a boat. Here, I'll be describing a model that we built to consider this goal that I have up here on this slide. And in our model, we focused our attention on 4 very serious invasive species here within the state of Minnesota. These 4 species were zebra mussel, Eurasian water milfoil, starry stonewort, and spiny water flea. Even though there are many other invasives present in our state, these are the ones that get a lot of our attention here at MASERC because they are particularly bad. We know relatively a lot about them. And in this particular case, we know they spread particularly well thanks to boats. So thinking about this in terms of boats, these are logical species to choose to focus on. I said earlier that we as a state are trying to intercept as many risky boats as we can as they move between lakes. What do I mean by intercepting boats? Well, I suppose we could mean a lot of things by that. But one thing that the state of Minnesota does is deploy watercraft inspectors to individual lakes. During a watercraft inspection, inspectors check out boats coming into or off of a lake to see if any invasive species are trying to hitch a ride on that boat. If any are found, the inspector can help the boater remove them, or if that just isn't possible, at least they can warn the boater about them, or even in rare cases, deny them access to a lake. So that's kind of the goal, right? Block invasives and invasive carrying boats wherever we possibly can, either by removing those invasives or hopefully ensuring they're never there in the first place. The question, though, is how do we know where we should be placing these inspectors to intercept as many risky boats as we can? That's the challenge, one that we might try to solve by using a model, in particular, an optimization model like the one I'm going to be describing here. Now is a good time then to mention that when we are trying to craft a complex model like the one I'm going to show you, we often have to make a few simplifying assumptions about how the real world works to make the problem simple enough for a model to be able to actually solve. Here we're going to meet our first such assumption from our own model, and that is that inspections are perfect at mitigating risk. If you have an inspector at a lake, he or she will intercept every risky boat coming into or out of that lake without fail. Now, we know that isn't true. No inspector is that good, right? However, we're okay assuming it anyways, so long as it's not wildly false either, which in this case it probably isn't. Besides, it's really hard to know what factors would cause an inspector to be less than perfect. By making this assumption here, we get around having to try to include all of those factors in our model somehow, which would make it much more complex. I also brought up this assumption at this moment for a second reason, though. If inspections intercept risky boats both coming into and out of a lake, then inspecting one lake can actually be good for other lakes too, right? An infected but inspected lake will, we assume, not be able to spread invasives to other lakes. It's like that lake is sick, but it's kind of in quarantine essentially. And that's a key concept that our model thinks about. So, one important consequence of that assumption is that it makes deciding where we should be putting inspectors actually a little trickier in practice, right? With this assumption in place, to intercept all the risky boats moving between any 2 pair of lakes, you actually don't need to inspect both lakes. You just have to inspect one or the other. To inspect both would actually be redundant. You'd be inspecting the same boats twice. You'd be inspecting them when they're coming out of the first lake and when they're coming into the second lake, which we assume isn't necessary here. So that complexity actually makes this the perfect kind of puzzle to try to solve using a particular kind of modeling tool, and that's optimization modeling. So let's pivot now to start talking about how these types of models work using our real life model as an example. The first thing any optimization model needs is a set of inputs. In other words, we need to give the model some data related to our problem that we want it to solve. And the first input we gave our model is something called an edge list, which sounds fancy, but it's really not. It's just a list containing 3 simple pieces of information. For every pair of lakes that boaters connect via trips, how many boats are moving into the receiving lake each year? So our edge list had 3 columns. It had a column denoting which lake was the donating lake or the from lake in a pair. We had a column telling us who the receiving lake was or who the to lake in a pair was, and then a column containing the number of boats moving in that particular direction per year. So This is called an edge list because connections like these trips are called edges in the branch of science that studies networks. And lakes connected to each other by boaters, it's just that, it's a network. So hence an edge list here. This is one of the most pivotal inputs that we gave our model. Recall at this point that our first assumption was that inspectors are perfect, such that inspecting a lake intercepts all risky boats coming into or out of that lake. Now that we've introduced the idea of edges, if we think about this assumption in terms of edges instead of in terms of lakes, we can assume that so long as we are inspecting either the donating lake in an edge or the receiving lake in an edge, we are inspecting all the risky boats moving along that edge, and we only need to do one or the other. This actually allows us, oh, I should say here's an example. Let's say we knew we were inspecting lake number 3. We could go to this edge list now and find every one of the rows that contains lake number 3. And we could say we are successfully intercepting boats along all 4 of these edges. These 3 where lake 3 is the receiving lake, and this one where lake 3 is the donating lake. We could then add those numbers up and figure out how many boats we're actually intercepting. So all of this allows us to state our goal or our objective, which is the second thing an optimization model needs, in a mathematical way, right? We want to be intercepting as many risky boats as we can along as many edges as we can. That is, we want to maximize this sum that we have created here using the edges and lakes that we've decided to inspect. We want that number to be as high as possible because that would be optimal, right? Hence the term optimization modeling. It turns out that if you give a computer a problem like this one and enough time to solve it, it can actually find, thanks to mathematical wizardry, a provably optimal answer. It can tell you what lakes you should be intercepting or inspecting and how many edges you should be intercepting as a result of doing that. It's very cool, really. So our model is going to be searching to find the optimal set of lakes to inspect so as to be able to intercept as many boats moving along as many edges as possible. At the same time, we're going to tell it something very important, and that is that it cannot choose to just inspect every single edge or every single lake. That would obviously be our best option, but it's just not realistic. We have 12,000 or so lakes in the state, right? So it's pretty unrealistic we'd inspect every single one of them. It's also not a terribly interesting answer to our question, right? Because we don't need a model to tell us that's our best option if we could do it. So we need to give our model a third important thing, and that's something called a constraint. A constraint is a rule that the model cannot break while it is searching for the best solution. So here we'll tell the model that there is a max inspector budget, capital B, and it cannot inspect more lakes than the budget allows it to do. So you can see B's relationship up here controls which lakes get inspected, which controls which edges get inspected, which controls how many boats we're ending up intercepting. All right, before we go any further, I want us to pause and consider the scope of the problem that we've created so far for our model. With 12,000 different potential donating lakes and 12,000 different potential receiving lakes, that would mean there's 144 million potential edges that exist within our state. It's actually worse than that, though, because these have a direction. Boats can go from A to B or from B to A, and those two numbers don't need to be the same. So there's actually 288 million potential edges we have to consider. Even for a computer, that's a huge number of options to consider and search through. So we need to make our problem smaller somehow to make it easier for the computer to solve. One key way we might do that is by making another assumption. And here we did. We decided that not all edges that exist actually matter. Sure, there could be 10,000 boats moving between a specific pair of lakes every year, which would be a lot. But if those boats aren't risky, they don't matter for our purposes, right? Because they're not spreading invasives then. So recall that risky boats are those moving from an invaded lake to an uninvaded one, and thus they can spread the invader. We need to help our model understand which edges and boats are risky so that it can ignore all the boats that can't. And we decided to do this by feeding our model another input. This input is a list of the infestation statuses of every lake in the state for every invasive species we care about. And I mentioned here that we have 4 that we care about. So in our particular case, this input looked like a really long and sort of scary looking table. It had a row for every single edge that existed, so every pair of two lakes that we could imagine being connected, and then it had 8 columns. And these columns held the infestation statuses of the donating lake in that edge for each of our 4 species K, which are represented here as K1, K2, K3, and K4, and the infestation statuses of every receiving lake R for those 4 same invasive species. So if a given lake is infested with a given species, that corresponding cell is going to hold a 1 and it's going to hold a 0 otherwise. And I know it's tricky thinking about all of this in terms of zeros and ones, but that's a very easy way to convey this information to a computer. So that's why we have to do it in the ways that we're doing it. What we're just ultimately trying to tell the computer here is who's contagious with each invasive species and can thus spread it, and who's susceptible to each invasive species still and can thus catch it. Now, if we stop here to think about it, for any one edge and any one invasive species, there are 4 possible scenarios we might encounter. We need to figure out which of these 4 scenarios are risky ones and which aren't. So let's start by looking at the first scenario. The first scenario is that neither lake has the species that we're thinking about. So in our little input table here, both of the values are going to be zeros. In this particular case, yes, the receiving lake is still susceptible to this invasive species, but the donating lake doesn't have it and thus can't spread it. So this would not be considered a risky edge. We could ignore it for that purpose, at least for this species. In the second scenario, both lakes have the species that we're thinking about, which means both values in the table are 1. So here, the donating edge is contagious, but the receiving lake isn't. It's not susceptible. So again, this would not be a risky edge. In the third scenario, the donating lake doesn't have the species we're thinking about. That's a 0, but the receiving lake does have it. Well, gosh, this is the opposite of risky, right? The wrong lakes here are susceptible and infectious. So we wouldn't consider this edge risky either. In the fourth scenario, we have one that's the opposite of the third scenario. Here, the donating lake does have the species, it's a 1. The receiving lake doesn't have the species, it's a 0. This edge is the one that's going to be risky. So, in essence, what we need to do to figure out which edges matter and which boats matter and which don't, we need the model to go through this table and find this pattern. A 1 for the donating lake, a 0 for the receiving lake. Now, we could do this sort of manually, or we could check this by ourselves, but it would take a really long time. It's much easier to have the model do this checking for us in some way. And it's even more convenient when you consider that we can use a little math trick here to have the computer search for this pattern. Turns out that if you multiply the donating lake's status by 1 minus the receiving lake's status, which edges are risky becomes very clear. And so I'm going to show you this. I'm going to again put the 4 scenarios we just outlined back up here, but now I'm going to do it in terms of math. And what you'll see is the donating lake status in blue, the receiving lake's status in green, and the outcome in black. And what you'll see when I put this math up there is the only time we get a black number 1 here is in that 4th scenario where the donating lake is a 1 and the receiving lake is a 0. So it turns out that if you just do this mathematical equation here for every species combo for every row here, you'll quickly be able to have the model do this arithmetic for you and throw out every edge where you don't get a 1 for this calculation. The only caveat here I should mention is that we're thinking about 4 species and not 1. So we have to tell our model that a 1 for even one of these 4 species is bad enough for the whole edge to still be considered risky. We don't even want to spread a single species if we can prevent it. So a 1 in any of these 4 pairs of columns would be bad enough for an edge to be kept. All right, now that we understand what inputs we've given our model and what problem it's trying to solve, we can talk about how it actually solves the problem, because that's pretty interesting with optimization models. So to do that, our model needs another input from us. It needs a set of decision variables. And in this case, we actually gave it 2 decision variables. Ones we're calling E sub I and L sub J for short, and they kind of sort of look like the boxes I just put up here on the screen. What is a decision variable? Maybe of all things in optimization modeling, this is the trickiest concept to understand. You can think of each decision variable we create as like a house that's full of switches or values that the model can experimentally play around with in an attempt to find the best solution available. So here we've made our decision variables binary, which is just a fancy way of saying that the values inside of them can be flipped between ones and zeros, and that's it. So you can think of them as like big boxes full of sets of light switches. Each switch can be flipped on or off, and the model is just trying to figure out which configuration of ons and offs is best, subject to any constraints that we've given it. So I is our subscript in our model for edges. So the I subscript on our E decision variable means that we have I number of switches inside of it, one for every risky edge that we've identified in our edge list. If the switch for a particular edge is 1, that means we've decided that edge is on. We are intercepting the boats along that edge. A 0 means it's off. We're not doing that. The J subscript in our model, meanwhile, corresponds to lakes. So that means that we have J switches inside of our L decision variable, 1 for every lake we have. If we're inspecting a lake, its corresponding switch is 1 or on inside of L. It's off or 0 if it's not. Again, thinking in terms of zeros and ones, maybe not the most intuitive thing for us to do, but very easy for a computer to do. Because intercepting boats along edges is good, we want as many switches inside of E to be 1 as possible. Every single one we turn on inside of E means boats we're intercepting. However, we don't actually pick edges to inspect, do we? We pick lakes to inspect. So what the model is really trying to do is figure out which edge lakes need to be on inside of the L decision variable, and that will tell it which edges it can turn on in the edge decision variable. Unfortunately, this is not something that our model could necessarily do automatically. We need to tell it exactly how it would do that by establishing a connection between these two decision variables. And we will do that by establishing another constraint. An edges switch can be 1 if and only if at least one of its corresponding lakes, either the donating lake or the receiving lake, is getting inspected, and thus its corresponding switch is 1. So to show you what this looks like, let's imagine the model is going to try out turning on the switch for lake number 2. It turns on the lake switch for lake number 2. It then goes down into the table here that we've shown, the edge list, and tries to find every single edge that involves lake number 2, either as the donating lake or as the receiving lake. Once it finds those, then and only then is it allowed to go over to the edge list decision variable and turn those corresponding switches to 1, which would then allow these 4 sets of boats to be considered intercepted. So we start with figuring out which switches need to be on an L. That tells us which switches are on an E. That tells us how many boats we're intercepting. So we just need to do this sort of set of decisions and playing around until we find the best possible solution that gives us the biggest sum of inspected boats that we can possibly manage. So the more L's we are allowed to turn on, the more E's we will be allowed to turn on. And the more E's we turn on, the more risky boats we are intercepting. So that's essentially how our model is thinking about its decision making and its experimentation in words. The challenge is we need to do better than words. We need to find a way to say in math what I just said in words so that the computer can solve it. Mostly this comes down, again, to formulating the constraints I've already explained in a mathematical form. So that's what we'll do here. We'll start with the easier of the two constraints that we've met so far, right? The first of these is involving our budget. We need to make sure that more lakes aren't inspected than we have a budget to inspect lakes. So what we tell our model here is that it needs to sum up the decision variable L. It needs to find all the switches in there that are on, and that number cannot exceed our budget. Hey, you can't intercept more or inspect more lakes than you have inspectors to be able to do that with, right? So we've essentially just created a sum and an inequality equation up here that the model has to be checking as it's going. Any solution that would violate this rule can't be considered. That's the easier of the two constraints, unfortunately. The other one is that we need the model to know it cannot turn a switch on for an edge unless one of its corresponding two lakes is also being inspected, as we discussed on the previous slide. And unfortunately, this isn't actually something our model would know how to do at present, because it actually doesn't automatically know which edges correspond to which involved lakes. So we need to give it a third input to help it do this. And we called this input matrix V. V is I rows, so it has a row for every edge, and J columns, so it has a column for every lake. Inside of V, there are two values in every row that are a 1. It's a 1 wherever the receiving lake is involved in that edge. It's a 1 where every donating lake is involved in that edge. So we have 2 1s in every row, and the rest of the values are 0. In other words, we're basically just telling the model here what edges belong to what lakes. So this allows the model to then be able to connect our constraints here to not place any switches as 1s inside of E that it's not allowed to do. So thinking about the same constraint that I talked about on the previous slide now, a value or a switch inside of E can only be 1 if and only if the LJ is 1 for at least one of the lakes that belongs to that particular edge, either it's donating lake or it's receiving lake. So thinking about this again, if we've chosen to inspect lake number 2, what the model will then do is come down here and figure out, okay, what edges is lake number 2 involved in as either the donating lake or the receiving lake, because that value will be a 1 here. And you can see that the model, according to V, thinks that lake number 2 is only involved in 3 edges in total. Only if those values are 1 can these values inside of E be 1, and thus the boats associated with those edges be considered inspected. So kind of a tricky notion. This is probably the part of the model that took me the longest to figure out. I don't want to dwell on the slide for very long, but we've been talking about the model in terms of sort of like words and equations so far. But I wanted to note that the model, when we actually went to run it, we ran it in R using 2 packages, OMPR and OMPR ROY, which are available for free. And I will say that despite the fact that maybe the model sounds complex in some ways, it actually doesn't involve a whole heck of a lot of code to write. You can see that it only took 8 lines or 7 lines of code to be able to create this model. And some of the pieces in this code you might actually be able to now recognize, hopefully based on the script descriptions I've given you on the previous slides. So these first 2 lines after the first, those are just us setting up our decision variables. You can see I've noted that they are binary here, and you can see that there are E sub I and L sub J, exactly as I've described them up to this point. That more complicated of the 2 constraints, where an edge can only be inspected if one of its involved lakes is being inspected, that's that 3rd line there. So V is our matrix, L's our lakes decision variable. All of that places a constraint on what E can do. So that's essentially what that line of code is like. And maybe this will make you feel better, maybe it won't. But I think just figuring out what that line needed to be probably took me 3 days of work. So not to say that this is necessarily something that's easy and intuitive, although it is definitely possible to get the hang of it over time. The simpler constraint where we have our budget, that's the 4th line there. Basically, don't let the sum of L be greater than B, which we've talked about. That second to last line is us setting our objective. Multiply every edge that's on by the number of boats involved in that edge and try to maximize that sum. So hopefully that makes sense now. And this last line just tells the model how to actually solve this. So I'm telling it here, use the Symphony solver, which is one of, I think, 16 different solvers that these packages have. One nice feature of Symphony is that you can set a time limit. Try to find the optimal solution for an hour and tell me what you've got at the end. You can also set a gap limit, which is how close to the optimal solution you feel like you need to be before the model can stop. And so here I actually told it, once it's within 1.5% of the optimal solution, you can stop looking. So you can actually run a model like this in less than an hour if you want to. And it will be darn close to the right answer, if not the right answer. So there you have it, a real optimization model in the flesh. Now in our project, we actually built and ran 3 subtly different versions of this model that I just described so that we could actually compare them. And I want to talk about those 3 versions now because I think they're very interesting. In the first version, which we call our statewide model, we imagine that there's an all-knowing, all-powerful person working for the state of Minnesota who knows about all the risky boats in the entire state and places however many inspectors they get to place in such a way that they shut down as many of those risky boats as they can. So they they may have a limited budget, but otherwise they can place inspectors wherever they want. And so not surprisingly, we might consider this to be a pretty close to optimal outcome, right? However, it's pretty unrealistic in some ways. It's not really close to how things actually work in the real world. So to compare to that situation, we also developed a county model. This is where we take that statewide budget, capital B, and we divvy it up into many smaller budgets, lowercase b, that we give to each county to spend. We then assume that each county will spend that money on inspectors, and we assume they will do so in a very particular way, which is to say we think they will spend them defensively and inwardly. And I want us to think about what I mean by that. First, by defensive, I mean that a county does know about and does care about risky boats that are coming into it from other counties. So to use a sports analogy here, counties would play defense and try to block other counties from infesting their lakes by sending boats into them. By inward thinking, though, we mean that a county does not care as much about risky boats it might be sending out to other counties. It doesn't play offense in this way, which is rational given that every county is going to have tight budgets and they need to spend them in a way that maximally benefits themselves relative to others. So, how do we actually build our county model? How do we go from a statewide model to a county model? Well, it's like we take the large problem I've described on the previous slides and we chop it into 87 mini problems for every individual county that we're looking at. So every new county that we're looking at, we go in and we chop out all the lakes in our edge lists and our decision variables that aren't in that county. We chop out every edge that doesn't involve a receiving lake in that county. And so then we end up with smaller decision variables and smaller edge lists and a smaller problem to solve. We solve that problem then for every individual county separately, and then we add up the total number of boats we get at the end of doing that. So I want us to consider here that a county may still, for inward-facing reasons alone, still choose to inspect a lake that sends a lot of risky boats out to other counties, which sounds offensive, right? And by doing that, it actually helps those other counties out. And that benefit is one that will show up in the totals that we get. It's just that counties aren't factoring those extra risky boats blocked into their decision making. It's like the counties have a pretty narrow focus on their own interests, like they have blinders on. So this is probably going to be a less optimal solution than the statewide solution. And so it's also more similar to what's happening in real life. So we might call this the status quo model or the status quo outcome. So that's the second model that we built. There's a third model, and it's very similar. We call it the collaborations model. And the only difference here is that in this one, we allowed some counties to team up. Within each team or collaboration, all the inspection stations that would have gone to the member counties now go to the whole team instead. And then that team spends that collective budget in the exact same way a county would normally do it, defensively and inwardly, except that it gets to consider the health of all of its lakes in all of its member counties, not just in any one county when it's making its decisions. So a collaborative's perspective is wider than that of any one of its counties. So you can think of these teams as kind of like super counties. We might assume that by allowing counties to team up in this way and think more broadly, the outcome is going to be closer to optimal than if we only allow counties to pursue their own narrow interests. And so that brings us to the 2 questions that we designed our model to answer. The first of these is, how much worse is this status quo county model that we built versus the statewide optimal model? How far away from the optimum is what we are basically doing now? The second question we had is, how much better would the collaboration model be than the status quo model? Would it be worth it to encourage some groups of counties to team up and think collaboratively? And since these differences in A and B here might depend on how big our total budget is for inspectors, we needed to ask each one of these questions at a range of potential budget levels. So that is exactly what we did. So what did our models tell us about these questions? Well, let's go ahead and take a look. Here is a graph that I'm about to put up here on the slide that shows how all three of the models performed at each of a bunch of different budget levels. So on the x-axis is our budget constraint. How many lakes could be inspected statewide, whether we allocated them statewide or by county? You can see that we ran each model at a range of 20 or more budget levels, which is represented by the dots here in our graph. On the y-axis is the total number of risky boats inspected as a result of the lakes that we've chosen to inspect. And as you can see, the statewide model, the all-knowing hero model, does the best, which is maybe not too surprising. In fact, it even suggests that we could intercept all or nearly all of the risky boats in the state by just inspecting about 500 or so of our 12,000 lakes, which is pretty remarkable. Meanwhile, our county status quo model does the worst. It's lower than the statewide model, even at low budget levels. It rises less quickly than the statewide model does. And it indicates that even with 700 or so lakes being inspected, we still wouldn't be intercepting 100% of the risky boats out there. Overall, in fact, it's about 20% worse than the statewide model at the point where that gap is the largest. So it's certainly not terrible, but it suggests that there is room for improvement over the status quo. We might ask, what are causing these losses in the county model versus the statewide model? And there we think there are two major factors that we can consider. First, some counties may be playing defense, inspecting lakes with a lot of incoming risky boats, but that means they might be ignoring lakes where there are even more outgoing risky boats that aren't getting inspected as a result of that. So we're missing some lakes from an optimization standpoint because we're focusing on playing defense instead of on playing offense at the county level. And the second reason is that we might end up with some counties that are placing inspectors sort of redundantly, right? Remember that counties here are not coordinating. So they may choose to independently inspect both the donating edge and the receiving edge lake in a given edge, which, as we've talked about thanks to our assumptions, is redundant. So one of those inspectors is getting wasted whenever that happens. So those are the two reasons. And both of those reasons are things that might be somewhat better in the collaboration approach. So how much ground do we make up by allowing some counties to coordinate? Well, in our particular model, we only let 9 counties team up to coordinate. We allowed a team of 6, which is shown in green here on this map, and a team of 3, which is shown in pink. And by allowing just those 9 counties, albeit with a lot of risky boat movements, to team up and think collectively, our collaboration model made up about 30% of the difference between the status quo and the statewide model at its widest point. And that's pretty cool to us, right? That suggests that even a little collaboration could get us a long way closer to optimal. And lest anyone think that we're cherry picking here, I will note that we estimated about 452 lakes were inspected statewide in 2017. So thinking about this particular problem in this region where those large differences exist is probably the right thing to be doing. All right, so I've introduced you to invasive species and inspection station placement and optimization modeling in this video. Hopefully you feel a little bit more informed about each of these 3 topics and how optimization modeling may help us address the spread of aquatic invasive species. I'm going to close here with just a quick slide on some takeaways that I hope you'll take with you from this video. The first of these, and maybe the most important, is that optimization modeling is a cool and powerful tool for guiding, planning, and decision-making, especially when the right or optimal choice isn't necessarily obvious. Even big models like the one I've described here can run quickly. 24 hours, 12 hours, 4 hours, even 1 hour, you can get the provably optimal solution or close to it. Secondly, R can be used to fit them. So optimization modeling sometimes does, or has in the past, I should say, required proprietary software that costs a lot to buy and keep. R, meanwhile, is free. So while R does have its limitations over those other software platforms, it's also free. So a lot of people, you could download it today and be running these models if you wanted to without spending any money. And while optimization modeling is challenging to learn at first, it doesn't actually necessarily require super complex thinking to be able to craft a really cool model. It just requires you to be able to think in terms of switches inside of decision variables and algebraic expressions with inequalities in them, and sometimes for more complicated models like ours, matrices and multiplying matrices together. So things that, at least in my case, I learned in high school, although I hadn't used them much since then. So not necessarily super complex thinking. You're not going to necessarily, for example, need to do any calculus or integrals to be able to set up a model like this. So it's accessible, is what I'm trying to say. The second takeaway I want to focus on here is that the movements of invasive species around the state are significant. And that's why we need tools like this to help us think about how to combat those movements. We would estimate that 800,000 risky boat trips occur every year within our state, and about approximately 25% of them may go unintercepted at present, and maybe in some ways that's a conservative estimate, which means a lot of lottery tickets are being bought for species within our state every year. So we need to be thinking about how we could get closer and closer to making that percentage 0% if we want no more new invasive species to spread and establish. The last takeaway I want us to leave with here is that by allowing and encouraging some jurisdictions to team up and work together for their own collective interests rather than their own personal interests, it looks like we could perhaps get as close as 50% closer to the optimal level of boat interception within the state without changing the total budget for inspections at a statewide level, right? There's always limited money. So just by changing how we think about that money and use it, the fact that we could maybe get as close as halfway to the optimal solution is pretty exciting. So I thank you for paying attention and watching this video series, and I encourage you to reach out if you have more questions about optimization modeling. I'd love to be able to answer them for you.